Welcome to a u-Substitution challenge problem. So in this example, we are going to evaluate the indefinite interval that is the integral of, in the numerator, 2x cubed plus 11x squared plus 21x minus 15, all divided by, in the denominator, x squared plus 6x plus 13. So as a general rule, if we have equal or higher power in the numerator than the denominator, we should go ahead and run long division to simplify our numerator. So we're going to start off by run long division. To simplify the numerator. No reason to have a more complicated numerator than necessary. So in this case, we have our numerator 2x cubed plus 11x squared plus 21x minus 15 inside. Then we are dividing that by x squared plus 6x plus 13. X squared goes into 2x cubed. 2x times 2x times x squared would be 2x cubed. 2x times 6x would be plus 12x squared. 2x times 13 would be a plus 26x. And then we are going to go ahead and subtract this all. Doing our subtraction, the 2x cubes cancel. 11x squared minus 12x squared is a negative x squared. 21x minus 26x is a minus 5x. And then we go ahead and pull down our minus 15. X squared goes into negative x squared and negative 1 times. Minus 1 times x squared is negative x squared. Minus 1 times 6x is a minus 6x. Minus 1 times 13 is a minus 13. If we go ahead then and subtract all of this, we wind up getting negative 5x minus 6x is x. Negative 15 minus negative 5x minus negative 6x is x. Negative 15 minus negative 13 is a minus 2. So we wind up getting, as our simplified answer, we have 2x minus 1. The remainder is an x minus 2, which is still being divided by that x squared plus 6x plus 13. So our integral now becomes we have the integral of 2x minus 1 plus x minus 2 is our new numerator over x squared plus 6x plus 13, then dx. 2x minus 1 is quite simple to integrate, so we can split this up. We will have an integral of 2x minus 1 dx plus an integral of x minus 2 over x squared plus 6x plus 13 dx. Now, having an x in the numerator lends itself actually to a just basic u-substitution problem here, since the derivative of x squared plus 6x plus 13 would drop us down to x. So an x in the numerator sort of leans us toward basic u-substitution. since the derivative of x squared plus blah, 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 we'll have 2x plus, etc. Right? Now, whether this works out perfectly is a whole another question. So in this case, let's go ahead and just see what happens. So if we set u to be the denominator, of x squared plus 6x plus 13, then we have that our du is 2x dx. Sorry, not 2x dx, I missed the remainder. 2x plus 6 dx. Or x plus 3 dx is equal to 1/2 du. So essentially at this point, we need the numerator to be some number a times x plus 3 or times 2x plus 6 for the u-substitution to work out. So what we are going to do is we are essentially going to split the numerator into a component that is a multiple of 2x plus 6, and then the remaining component. So we are going to split the numerator. So we had x minus 2 over x squared plus 6x plus 13. Let me just shift that a little to the side. We are trying to rewrite this as something times 2x plus 6 plus some other number all over x squared minus 6x plus 13. And the reason for this is this will land us on an a times 2x plus 6 over x squared minus 6x plus 13 plus a b times 1 over x squared minus 6x plus 13. This first component is perfectly set for u-sub. The second component can be forced into hopefully forced into an inverse tangent integral format. So in order for this to hold true, we have x minus 2 is equal to a times 2x plus 6 plus b. That means that x minus 2 is equal to 2 times a times x plus 6a plus b. If we match coefficients, we get that 1 should be equal to 2a, since the coefficient in front of x is 1. And then negative 2 should be equal to 6a plus b. 1 equaling 2a means a is equal to 1/2. So we have negative 2 plus 6 times, or sorry, negative 2 equals 6 times 1/2 plus b. that means -2 is equal to 3 plus b, or b equals -5. So at this point, our integral is now equal to the integral of, we have 2x minus 1 dx plus, we just found a to be 1/2. So plus 1/2 times the integral of 2x plus 6 over x squared minus 6x plus 13 dx. Then we have -5 times the integral of 1 over x squared minus 6x plus 13 dx. I know how to do those first two integrals now, so I'm going to do these in pieces. So integral of 2x minus 1 dx is just, we would go to x squared minus x, and then of course plus, we'll just call it plus c1. The integral of 2x plus 6 over x squared minus 6x plus 13 dx. Actually, let's keep the 1/2. So the integral of 1/2 the integral of 2x plus 6 over x squared minus 6x plus 13 dx. This was set for taking u to be equal to x squared minus 6x plus 13. I apologize. These denominators should have all been plus. It should have been x squared plus 6x, x squared plus 6x, x squared plus 6x, x squared plus 6x, all denominators I have written. Should have been x squared plus 6x plus 13. All right, so we set u to be x squared plus 6x plus 13. Our du was our 2x plus 6 dx. So our integral simply becomes 1/2 the integral of 1 over u du, or 1/2 natural log the absolute value of x squared plus 6x plus 13. Let's do u first. 1/2 natural log absolute value of u plus c2, or 1/2 times the natural log of the absolute value of x squared plus 6x plus 13, and then plus c2. For our last case, we're looking at a -5 times the integral of 1 over x squared plus 6x plus 13 dx. And I need to update my screen. All right, so during the integral of 1 over u, we had natural log of absolute value of u. So that led our 1/2 integral 2x plus 6 over x squared plus 6x plus 13 dx to be equal to 1/2 times the natural log of the absolute value of x squared plus 6x plus 13 and plus c2. So now moving on to our -5 times the integral of 1 over x squared plus 6x plus 13 dx. For this one, we are going to force uh, 1 over u squared plus 1 squared or plus a squared du format. So we will need to complete the square. So we have x squared plus 6x plus 13 is equal to something squared plus something. So x squared plus 6x plus 13, we are looking at x squared plus 6x plus blank. Then we have plus our plus 13 minus our blank. For that blank, we're going to divide that plus 6 by 2 and then square it. 6 over 2 is 3, squared becomes 9. So we are looking at a plus 9. To balance that out, we will subtract off 9. This first part becomes x plus 3 squared plus 13 minus 9 is plus 4, or x plus 3 squared plus 2 squared. So we are looking at negative 5 times the integral of 1 over x plus 3 squared plus 2 squared dx. We'll go ahead and set that x plus 3 as our u. That means that du is simply dx. And we are looking at a negative 5 times the integral of 1 over u squared plus 2 squared du. Here that 2 is our a. So we are looking at our inverse tan case with a equals 2. We get negative 5 times 1 over 2 times tan inverse of u over 2 plus c3. Plugging back in our u, we have negative 5 halves tan inverse of our u was x plus 3 over 2, and then plus c3. So putting these all back together, we have that our original integral, which was a long ways back, 2x cubed plus 11x squared plus 21x minus 15. So I have integral of 2x cubed plus 11x squared plus 21x minus 15 all over x squared plus 6x plus 13 dx is equal to our very first component of that integral was x squared minus x plus c1. Then we have plus the second component of our integral was a 1/2 natural log absolute value of x squared plus 6x plus 13 plus c2. We add on plus a 1/2 natural log x squared plus 6x plus 13 and plus c2. And then our last component, we subtract off 5/2 of tan inverse of x plus 3 over 2 plus c3. At this point, we can go ahead and combine our c1, c2, and c3. And we wind up getting that our integral is x squared minus x plus 1/2 times the natural log absolute value of x squared plus 6x plus 13 minus 5/2 times tan inverse of x plus 3 over 2, whole thing plus c. So this problem used most of the versions of u-substitution that we have available, or many of the versions of u-substitution that we have seen, plus some long division of polynomials. So this is one of the more complicated integrals that we can solve using u-substitution. In the next videos, we will take a look at definite integrals and u-substitution.